Welcome to the course on analog VLSI, and we are going to the series of OPAMP. Today is lecture 2. Myself, Arpan Deashi from Department of Electronics and Communication Engineering in RCC Institute of Information Technology, Kolkata, India. Welcome you all to the series of OPAMP lectures, and I am going to the lecture 2 after the initialization in lecture 1. In lecture 1, we have discussed about the foundation of the OPAMP, more precisely the differential amplifier circuit, the need of virtual ground, how a virtual ground is really made, what are the components including the sources, voltages, external biasing concepts, the passive and active devices, how they are utilized, what is the difference between the virtual ground and realistic ground or the actual ground, how it helps to make the op-amp circuit, that means the heart of the op-amp. And after that, I have discussed about the basic building blocks of the op-amp, the 5 fundamental blocks, and functionalities of each block. If you remember that I have discussed about the all types of compensating circuits, the differential transconductance stage, the buffer part, output amplifier portion, as well as the biasing circuit. And that's all for the previous class, that is the first lecture, which is basically set the tone of this today's lecture. Today is also the theoretical part that I will discuss, but it's something like that we are going to make it more a little bit towards the actual design purpose. And for that, in order to achieve the actual design and precisely the adjustment of the offset, which is one of the major requirement for op-amp based circuit application, I should better to cover the equivalent circuit, the different components of the equivalent circuit, what are required, and as well as I will move towards the design procedure or the different steps of the design. And these are the prerequisite once we will go to our actual design of the op-amp. So without making much delay, I want to just convey that we are moving towards the first part, that is the what are the components or the additional components required in order to make a practical circuit of an op-amp. Please consider that I am doing for practical circuit. The ideal circuit is not actually valid once you go for the calculation, because the infinite input impedance or zero output impedance you can't achieve. That's never possible. Whatever you can achieve is that low output impedance and high input impedance, and that's all. So if we want to go for that part, then I think the characteristics, the equivalent circuit of the op-amp are much more in requirement, and I should go for that. So without wasting much details, I am showing you the actual circuit of the op-amp, and that is the equivalent circuit. So if you have a closer look on the equivalent circuit of the op-amp, you will find that naturally the circuit is subdivided into many portions. So it is better to first consider what are the different parts and how it can be, why these components are required actually, and that's one of the most important part for analyzing the op-amp circuit. The triangle which is shown at the right part, that is the ideal op-amp. But what are the additional components required, I am showing with some diagram, and you will find that one resistance is connected after the output of the ideal op-amp, and naturally that output resistance, this is the practical output resistance or output impedance of the op-amp. So R0 should not be very large, it should be very small. However, you can't make R0 is 0. That means you have to consider the finite input resistance of the output resistance actually, sorry, finite output resistance of the op-amp, and your V0, that is the output voltage. You can only take the output voltage once the signal overcome the R0, not before that. Whatever in our theoretical op-amp circuit, we are generally accustomed to take the output voltage just after the op-amp. This is not the practical circuit. Or however, you have to consider that there should be some sort of output voltage in op-amp. Next, I am going to the extreme left, that is the input, and naturally, you know that in the last class, I have discussed in details the virtual ground part where I have considered the differential amplifier circuit. And naturally, it should have two input sources, so Vi and Vj are my inputs. Fine, up to that, I think you won't find any differences with the theoretical op-amp input and the practical op-amp input. Because simple, the Vi and Vj, these two inputs are also required for your theoretical circuit. But after that, look, I am given a voltage controlled voltage source which is Vj by CMRR. And what is that Vj by CMRR? Naturally, you are adding one factor with the Vi. And addition of a voltage, as per Thevenin's theorem, if they are additive in phase, naturally it will increase the voltage value. So if Vi is increased, that means the difference between Vi and Vj, that will be also increased compared to the previous case. Now please think that if CMRR is very low, then Vj by CMRR is high, and that the addition factor will be much higher. And what is the significance? If the two voltage sources have a greater difference, then you will generally tend to consider the important voltage source, that means the additive part of Vi plus Vj by CMRR. That means the Vj, that voltage source, you may consider, I think, practically negligible. And a practically negligible voltage source, what it will be with respect to any analog or digital circuit or mixed signal circuit, if you have a familiarization with the VLSI also, that's why I have used the coin the mixed signal. Naturally, an insignificant voltage terminal means it's close to ground. But whether Vj is actual ground? Sorry, no. So it will be like a virtual ground concept. That means you are sensing the ground potential because Vj by CMRR is already added. And after that, from your classes of differential amplifier, you know that the differential amplifier gives offset null sort of voltage because of the three factors. What are the factors? The difference of the drain resistances, the differences of the aspect ratio, and differences of the threshold voltage. So what is the problem? You are considering VOS. That means this is the offset null. You can't say that the MOSFETs which you are using, according to our last class, if you have problem, you may visit to my YouTube channel in under the playlist of VLSI, and the foundation of op-amp, that lecture is already uploaded. So you may go through that. And you will find that there is a term, say, I am discussing about the virtual and actual ground and the differential input. So naturally, if you have two MOSFETs, their threshold may not be exactly same. Their aspect ratio may not be exactly same. And I will discuss at the last part of this lecture, I will discuss the design of the aspect ratio or the choice factor, how it critically depends on the other specifications. And the RD, two resistances, while you are making a circuit, the integrated circuit, you can't say that those the drain resistance exactly same. So there may be a offset null sort of thing, and you have to consider, naturally, as per the Thevenin's theorem, all the voltages should be additive. And after that, no device can be noise free. It's never possible. So we may consider some maybe current noise source or maybe voltage noise source. Nobody can say. If it is a voltage noise source, it's very simple. the Vn square Maxwellian average, it will be added with the existing voltage sources. If it is current source, simple, you have to make Norton equivalent circuit and it should be a parallel connection or the connecting between Vi and Vj. So my In square and Vn square, these are the noise sources, whatever I have discussed. And after that, you have the drain resistance. So there will be Rd, and Rd will be parallel with the Norton and series with the voltage sources. And you may have some sort of differential capacitance. You can't say that I don't have a capacitance, it's a pure resistive or pure resistive value. Never. There is a chance of the capacitance factor, so you have to agree about the differential capacitances purely for the AC signal when you are dealing with. Naturally, there will be CD and it should be a parallel with RD. That means it forms a sort of tank circuit that controls the frequency. And after that, you will find in the top and bottom there are some input common mode factors. In your differential amplifier class, you know what are the input common modes. You are sorting the two inputs. So if you sort, naturally that will generate a resistance and capacitance. So I am giving RICM or CICM. Now after sorting, whatever direction you are giving voltage, either inverting or non-inverting, it will be same because you have sorted. So in both the sides, I have reflected the same common mode resistance and capacitance. And the point is the bias current, it may not be same. Though input common mode resistances and capacitance are same, but bias current is not same. Why? That's one of the major question. Now you will find that maybe there are two sinusoidal voltages exactly inverted, fine, the average will be 0. But if two sinusoidal voltages are not exactly inverted, which are giving by the common mode coming to the gates of the two MOSFETs, then there will be an average value, and that's why the Norton equivalent current source will be slightly different. So IB1 or IB2, the bias currents for the common mode circuit, which may be different when it is coming to Vi or Vj. And those factors are given at the top and bottom. So that completes your overall equivalent circuit of the OPAMP. So I am briefly discussing or recapitulating just again. The output section, we have to consider the output resistance and output voltage, which is R0 and V0. The input section, I have considered the offset null, which is VOS, and the voltage control voltage source, that is Vj by CMRR. In the practical op-amp, I have considered the noise voltage source and noise current source, which is average of Vn square or average of In square. And the differential section, we have a resistance and capacitances, which is Rd and Cd. We have a common mode section where input resistance and capacitance are RICM and CICM. And the bias currents at the two different sections are IB1 and IB2. So that completes your equivalent circuit for the op-amp. How to make a realistic two-stage equivalent circuit of the op-amp for practical calculation, that I will go for the lecture 3. But for lecture 2, you understand why the different components arises for a practical op-amp circuit which are generally absent in a theoretical circuit. After that, I am going to the design steps of the op-amp. There are 3 fundamental design steps. Number 1, decide a suitable configuration. Number 2, determine the type of compensation model. Compensation means, I am again referring my lecture 1, which is phase, frequency or current compensation. And the step 3, design device sizes for appropriate bias. So let me go just briefly mention what are the design steps. The first is decide a suitable configuration. How it will be? It's very simple. First, you have to consider the specifications and the boundary conditions. What are the specifications and boundary conditions? The gain, CMRR, maybe PSRR, power supply rejection ratio, slew rate, noise bandwidth, temperature range. These are extremely important. So you have to consider these specifications and boundary conditions. Then once you will get that, you have to choose the type of configuration, whether it is telescopic or folded cascade. Normally these two types of configurations are choosing for a double stage or a single stage op-amp. If it is required voltage to current and current to voltage conversion, intermediate stage, you will go for folded cascade. Otherwise, you will choose the telescopic configuration. They have their own advantages and disadvantages. And then a mode of design that is selected based on the application. What type of configuration is required? Basically, that gives you the pole zero configuration, the stability criteria of the op-amp. And once you know the pole zero concept, the location of them, you will find how the op-amp will behave, whether it will be stable, quasi-stable, unstable, how could I marginally make it stable, or everything. So once the first step is over, then you will determine the type of compensation. It may require phase compensation, the phase is deviated too much. It may require frequency compensation, frequency may change. It may require current compensation, the current fluctuates. So type of compensation is required. Once it is known, you have to achieve that type of compensation. And that's very important for design of the op-amp. And then you will go for design steps of op-amp. That is, you have to choose what sort of inputs are. It is DC, AC or transient. Depending on that and all those configurations and your specs and boundary conditions, you have to calculate WIL. That's extremely important. If I am going to the last part of my lecture 4, I will try to show a mathematical equation or a real design problem where you can calculate the values really, and you will get that how these values will be calculated. So I may try to show some data how the compensating capacitances can be calculated for realistic circuits. And once you know the threshold limit, you have to calculate the WIL. And then you have to go back to the step 1 again. You have to check that whether based on the WIL your specs and boundary conditions are all satisfied or not. Otherwise, again you have to optimize, go to the loop. Again you have to check the WIL and whether your layout design satisfies all the requirements or not. Once you can make a first-hand layout, you can go for a details layout. If your layout is fine, you may say my design is perfect now, hand over to the fab lab. And that's the design procedure of the op-amp. Based on the detailed calculation, that's a theoretical outline. I am not going into the detailed calculation, but once time permit in the consequent lectures, I will show how the data will be calculated. So up to that today, we have discussed the equivalent circuit and design procedure. In the next lecture, I will go for the mathematical analysis for stability of an op-amp based on your equivalent circuit. Thank you all and wait for the next lecture.